welcome to today's webinar. This is a second part of series which were focused on a ladder deck composite bridge design. Last week, some of you maybe presented or followed the last week presentation. You may remember that we covered different model types and their purpose, certain section and model properties which we will need to define or correctly set up for the composite structure. And we also discussed a push launch construction, a specific type of construction for which the ladder deck bridge is suitable. So today we will focus more on practical tools and tips for modeling such a structure in Midas. So we will follow up on last week's presentation, and we will look at the model setup, primarily using Composite Bridge Wizard in Midas. We also look at certain model properties similar to what we discussed last week and how to define them in Midas. And we will also cover construction stages, again, the push launch and the deck pour stages. So that's the outline for our today's presentation. And for those who missed last week webinar, just a brief introduction of myself. My name is Martin Bosak, and I've been designing bridges for over 15 years now. And over those years, I worked on various types of structures and a variety of projects, primarily in UK and Ireland, but also in Europe. Also, just an introduction of the company. Our company, I work at Barry Transportation, which is a sister company of JB Barry and Partners Consulting Engineers, local Irish engineering consultancy. And both companies, they work closely together, primarily on Irish market, but also have international presence over the years. And specifically, Barry Transportation is focused on infrastructure and transportation projects, so mostly roads and other transport or traffic projects. This webinar series is based on a project I worked recently. It was a 5-span steel composite ladder deck structure. And again, just as a reminder from the first part of the webinar, it was about 250-meter long bridge formed by 2 main girders, 13.5 meters apart in ladder deck arrangement. And the deck was made of precast reinforced concrete panels, which were made composite with the steel structure using in-situ concrete stitches. And the structure was built by a push launch method. Here are general arrangement drawings, maybe either to refresh your memory or provide an idea of the general layout, which was used as a basis for the structural model. So now we can focus on the first main part of today's webinar, and that's the generation or setup of the model in Midas. Usually the first step when we start a new model or set up a new model is the definition of material and section properties. And we will cover that in a little bit more detail later during today's webinar. But what I would like to point out is that we have an option in Midas to import model properties from another model. So we can import material, section, and thickness from an existing model. And that can be useful for a faster model setup. We can save time if we have similar sections or same sections defined from a previous model. We can also select which sections or materials we want to import. So that allows us kind of create a template file, so to speak, and maybe use that library of sections across different projects. It may speed up the model setup. For the next step, creating a geometry, instead of applying manual approach, so when we manually define all the nodes and line beams or plates depending on type of the model, or import the geometry from an external software, we can use a steel composite bridge wizard in Midas. And that tool allows sort of a parametric modeling because we can define geometry, support, model properties, and basic loads and construction stages within the wizard. They can be all saved in a separate file and recalled later. So this way we can adjust the model and create another model based on existing structure. We can create multiple different types of model very efficiently and very fast. The steel composite bridge wizard has 4 main tabs. That's layout, section, load, and construction stage. And last time we discussed extensively what kinds of models we may use for what. What's the purpose of the frame or plate or mixed model? And you can notice here that the item 2, that's the selection of model type. So we can select whether we want to create a grillage model, full plate model, or some sort of a mixed model. And because everything else is basically the same, our span arrangement with the maybe support conditions, the loading, this way we can very efficiently and very fast create different types of models we need for our design and analysis. The model parameters can be saved separately or loaded from a previously saved files. And throughout the wizard, there are a number of schematics and illustrations which serve as a guide to help us in definition of specific parameters. So for example, here, if we want to model the substructure, there are guides to show what parameters we need to enter into the wizard. In the section part of the wizard, we define number and spacing of girders, distribution and type of cross beams or cross girders, and main girder details. Maybe if we keep in mind our structure I showed earlier, our twin ladder deck bridge with two main girders, there may be a question, why is there here 7 number of girders? And that's to overcome certain limitations of the wizard. So we know we have 2 real main girders in the structure, but because our structure has steel end cantilevers, because the cantilever is too long for a concrete only section, we need cross girders to run also outside main girders as cantilever. And because the wizard can only create cross girders or cross beams between main girders, we need extra sort of dummy girders at the edges of the structure, so we can have proper cantilevers modeled within the wizard. And also another limitation is that the wizard can only work with symmetrical section, so our deck, which is part of composite section, needs to have the same width of the flange on the right and on the left, and that limits the main girder section. So we need extra longitudinal girders to model the internal or middle part of the deck between the girders. And also it will help for correct load distribution during construction. So that number of girders we define includes not just the two main girders, but also some auxiliary or dummy girders, which help us in modeling. Also, one good tip or option we have in the wizard, that the cross girder spacing can be entered separately for each span. And again, if we have structure like our structure where there are 5 spans of different length, and cross girders have different spacing at each span, we can enter divisions in each span. In this case, we had first spans 11 cross girders, in the second spans 12, third and fourth only 10, and last span were 11. So again, that simplifies the definition or setup of the geometry. Also, for the cross girders or cross beams, for ladder deck bridge, we would primarily use a single beam type. So the truss bracing, as shown in the guide for the bracing type, it's more suitable for multi-girder structure, while for ladder deck with the long cross girder, we want to use a single beam, which will be in most cases also a plate girder. And these guides, again, may help in setting up all those dimensions and spacing and so on. On the loading part, we can enter the construction loading, the superimposed dead loads and other permanent loads, and also select the type of load distribution. That's point number 9 there. For ladder deck structure, it's useful to leave this box blank so that the load is distributed not equally to all girders, but according to real spacing. because we said we had some dummy longitudinal girders, and we don't want them to attract the same load as the main girders. So that's just a setting which is useful for this particular type of model. In the construction stage setup, it is assumed that all steelwork is activated at a single stage, and the deck is constructed in several stages. And we can define how the deck is assumed to be poured. There's this dialogue where we can define the sequence and lengths of different parts of the deck, and that's then reflected in those stages, which are generated automatically. So when we set all these parameters in the wizard, it may take maybe even less than an hour. It's very fast once we have the section properties set up, and once we know the geometrical arrangement. Then in the end, we have a complete model with the geometry, permanent loads, and construction stages generated. But if you look closely at this model, you may notice that few things are not right. For example, the wizard created supports at each girder, including our dummy girders. That means that some of the supports are redundant and need to be deleted. Also, since the wizard doesn't support tapered sections and our cantilever is tapered, the cantilever section needs to be replaced with a tapered section. So after the model generation, we may manually assign different section to the cantilever. Also know that for the grillage model, all main girders are created as composite section, and on this screenshot you can see that the deck slab portion of the composite section is shown as transparent. There are a few more adjustments which we may have to do after the model generation, and one of them is introduction or definition of time-dependent material properties. The wizard does not include time-dependent effects, creep of and shrinkage. So although in construction stages we have option to define durations of each construction stage period, which serves as a basis for a calculation of time-dependent effects, we still need manually to define creep, shrinkage, rise in or development of compressive strength of concrete, and then create a material link between those effects and materials we have assigned to sections. But the finished grillage model may look similar like this, with proper sections and proper supports. Similarly, if we generate a plate model, again we may have to adjust supports, which are again created under each girder, adjust cantilever sections. But notice that here, if we create a plate model, the main girder is not a composite section anymore. It is just a steel girder, because the deck slab is created as a separate element using plate elements. So although, for example, in the wizard, we still use a composite section in the section tab in the wizard, the section is transformed or changed during the model generation to a steel only. So we don't need different kinds of section if we change the model type. Now we can go back and have a look at few model properties. We said that we can import section properties from a separate file. If we don't have them available from a previous project or the same model, we need to define them. So for using wizard or for the grillage type of model, our main girder section will be always composite section. So in the section definition, we go to Composite tab and select appropriate type of composite section. Preferably, it will be a type 1 composite section, which is basically a symmetrical section with the same flange width on the left and on the right. We also should set the basic model ratio by selecting the appropriate material for the concrete slab and the girder. We also have an option to include long-term model ratio so that the permanent loads, long-term effects are reflected in that different ratio of steel and concrete. And we want to align the section properly. Usually it will be either top or bottom of the section, so not a standard center line. There is also a type 2 composite girder available in Midas, which is asymmetrical section, although that would be more suitable for ladder deck girder because with the girders far apart, we would want longer portion of the deck on one side of the girder than on the other side. However, this type of section is currently not supported in the wizard. It's also not supported for the composite girder design tool for the Eurocode design. So although we may use the section in the model, it can be used for the analysis and for the results. But if we want to use other tools in Midas, it may be better to stick with the type 1 with the symmetrical section. And one note to the modular ratio, the long-term modular ratio would be useful primarily for uncracked sections, because in hogging region where this deck is cracked, we neglect basically the properties of concrete, so we wouldn't need this multiple modules of elasticity. We can check the section properties generated by Midas. So the before properties are steel girder only. After is the full composite section with the concrete slab using the transformed section properties, so using the short-term modular ratio, and the long-term will be again the transformed composite section using the long-term modular ratio. In previous part of the webinar, we discussed that since the main girders of the ladder deck bridge are spaced wide apart, in case of our structure it was 13.5 meters, we can't assume that full depth of the deck slab acts compositely with the girder, and that's because of the effect of shear lag. So Midas has a function for an automatic calculation of the effective slab width. It is in the wizard part of the program in Composite Bridge. And the procedure how we can calculate the effective width in Midas is that we enter the span information. So basically we select the full girder, all spans of the bridge, so that the software knows the span distribution. And then we select the effective width calculator, in which we define the spacing of shear connector. That's for the Eurocode. In other codes, it may be slightly different depending on the code requirements. And when we show calculation results, we will get a list of all elements and the real width of the flange and the effective width of the flange. In Eurocode, I showed it last week, there's a guidance or procedure how to calculate the effective width, and that's reflected in Midas calculator. So we can see that over the supports, the effective width is shorter, and in the span it is wider, and that can be seen on the output from the calculator. So at the internal support, the actual flange width is 6.4 meters, but the effective width only 3.46. And as we move towards the internal span, the effective width is increasing up to 5 meters, 5.033. Yeah. So the total slab width, which can be considered as acting compositely with the girder, will be this flange width, BM1, the distance between shear studs, and the other flange width on the other side. However, in many cases, because of the cantilever length or other effects, our actual slab width we are using may be shorter. So if the physical width of the flange is shorter than the effective width, then there's no reduction. So this calculator may be useful if we want to use type 2 section with the wide one flange, or if we want to check if there are any adjustments needed in our composite section. Another aspect of grillage and of composite section is the cracked concrete over internal supports. Again, we briefly covered it in last part of the webinar, that the section stiffness is affected by the cracked concrete over internal supports. In the literature and from practical modeling, it can be seen that this effect extends usually about 15% of the span length from the support. So this is where the section properties of our composite section are affected, and we can adjust them in section manager in Midas. So the procedure here is that we create a composite section which we will later apply or assign to the hogging region, those 15% each side of the support. We calculate the properties of cracked composite section in that hogging region. So basically section properties based on steel girder and the reinforcement in the deck. And then when we use the section properties of full composite section, so the transformed section with the concrete slab, we calculate the stiffness ratio and assign it to the composite section that's the tick after, because that's when the section becomes composite. It's important to remember that, yeah, we reduce the cross-sectional area, shear area, second moment of area, but we don't reduce the weight, because the concrete, although it is cracked, it doesn't really contribute to the stiffness of the structure. It still retains its weight, and if we want the cell weight correctly applied, we don't want to reduce that. As I mentioned briefly when we talked about the composite section, we may want to use multiple modular ratios to take into account long-term effects. And actually in the section manager, if we tick those or set those long-term modular ratios, the program automatically creates the stiffness scale for these sections, reflecting the long-term stiffness ratio. So it can be verified basically here how the ratio is applied to the section, and it works similar way as with cracked section. If we model a plate model, so not a grillage with the composite section applied to line beam, we still want to take into account the cracked concrete. And the preferred method how to do it is in Midas, would be to use plate stiffness scale factor. So in Midas, in the properties, again, we can set the stiffness ratio for axial forces and for bending in different directions. So we want to reduce the stiffness of the deck slab in the longitudinal direction in which the concrete is likely to be cracked over supports, but we want to keep it uncracked or not affected, not reduced in the transverse direction of the slab, because that's usually uncracked. And then this scale factor again would be applied to those cracked regions, about 15% of the span length from internal support. I'm aware that in the previous webinar I recommended the other solution, which would be use of an orthotropic material. And although this would be a general method, which is software or analysis type independent, it is not as straightforward as use of the plate stiffness scale factor. So it is because the relationship between the Young's modulus and shear modulus and Poisson's ratio is not arbitrary. It is set by a physical definition of the material. So it may be difficult to correctly define those proportions and set especially the Poisson's ratio in different directions. So that's why it may be easier, and it is easier actually, to use the plate stiffness scale factor to account for cracked concrete. Now, in the last part of our today's webinar, we will discuss the construction stages, and that's the launch modeling and the deck construction. Launch is usually analyzed separately, either manually or using automatic stage generator. If we have only a handful of stages we want to analyze, it may be easier and simpler to do it manually. So we create supports for each steelwork position during the launch, and we can create either a separate model or create a few construction stages in which we activate different set of supports. For example, like on this slide, to model the longest cantilever during the launch, so before the tip of the nosing touches the next support. If we need to analyze, or if we want to analyze more positions of the structure during the launch, it may be advantageous to use automatic generation, although this is a little bit more demanding on correct setup, because the ILM wizard in Midas is more aligned with the with concrete structures, with the incremental launch method, and with the ILM structure wizard. It still works even for steel structure. So we create a temporary supports at the steelwork assembly area, and then we can define launch stages using the wizard. And if everything works correctly, it will create set of supports during the launch. The model looks like this screenshot. So there are loads of supports, but at each stage only a certain set of them is activated. We need to define the launching direction. So by default, it's from right to left. We tell the wizard or the program where to start. So that's the reference node. The location where the structure is at the start, that's the start node, and the end node is basically just the direction of the launch. The end result, how the launch changes, or how the structure location position changes during the launch, it can be seen on this short animation. So we can see that the cantilever increases until the structure reaches the support, and then again the tip moves forward. And that's just cycling through the different stages created by the ILM wizard. The deck pour sequence, it's the next part of the construction sequence after the steelwork is in place. If we use Composite Bridge Wizard, it will create basic deck pour stages automatically. So it's a little bit easier. There are certain limitations or things we need to remember, that the construction loading, like the wet concrete or formwork, is always applied on longitudinal girders by the wizard. So that's why for the ladder deck bridge, we want some additional dummy girders so that the load during the construction of the deck is applied on cross girders as it is in the real structure, where the cross girders are the load-bearing elements for the deck. And from cross girders, the load is transferred to the main girders. And the wizard allows certain flexibility in setting up those stages of deck construction. But if we require a different pattern, or if we need to do it manually, it's basically the same procedure. So the construction loading, and it could be a wet concrete formwork, or in case of our structure, it was a precast panel placed on cross girders. It is applied at relevant part of the structure. so maybe span by span or span section and support section separately. The important part, and that's basically the key consideration for setting up those deck pour sequence models, is that we need to apply the load and use the proper groups. So for the load, we use a load group. For the structure, which is activated or finished at certain stage, we use structure group. And we also need a boundary group if we have a separate deck, or if we use, for example, rigid links or some other types of supports. And that allows the activation and deactivation in each stage. So on this screenshot, we can see that at one stage the precast deck panels are placed in first two spans as a load, so they are not composite with the structure yet. In the next stage, in the first span, the panels, the in-situ stitches are finished and the panels become part of the composite structure. So the load is deactivated and the deck becomes finished, part of the finished structure, while in the second span, the stitches are still not finished, so the deck load is still applied as a load. So that's defined, if I go back here, in each construction stage as a active group or inactive group, and this would apply both to loads, to elements and boundary. So it is not difficult, but if we have more stages, if we need more stages, it may require more steps and more effort to apply those loads as they are applied at each stage. So that's basically all for today's presentation. There's not much, or it is not possible to cover everything within 45 minutes or so, but these were just the main considerations. I try to show how what benefits we have if we use the composite bridge wizard, what aspects we need to remember and set up for the model properties, for the section properties, and for material properties, taking into account cracked section, effective width, and also how to handle the construction stages. So I hope you found at least some of the information useful for your own professional work or modeling. If you have any questions, you can ask questions using the chat. I may answer some of them now, and the remainder of the questions will be available again together with the recording of the webinar later on the website. So thank you very much for your attention.